Right, yeah, thanks for the intro. So this is some joint work with Chandong Su that I'm presenting. And first I want to set the expectations for the talk. So in this talk, I'm going to present you intramorphic testing as a new general whitebox methodology to the test oracle problem. I will present the technique using illustrative examples. I will also provide a comparison with two other very general techniques, namely differential testing and metamorphic testing. And finally, I will outline the broad vision that we hope might inspire also future research on this topic. So let me first start with a motivating example, a bubble sort. And if you stare a while at this program, you might realize that we have a bug in it, right? We have here an index error. This index I should be J because we are doing a pairwise swap here. Now, how would you be able to find this bug? Assuming a developer perspective, the most obvious thing to do would be to write a unit test, right? We could take some unsorted input array. We could invoke this in-place bubble sort and then check whether at the end the array is actually sorted. And this would, of course, find the bug. But from a research perspective, we are interested in actually automating this process. So how can we do this? Basically, there are two challenges involved. First of all, we need an effective test case or input to the program. And then we also need a test oracle. And the focus of this talk will here be on the test oracle. A test oracle is a mechanism that determines whether a test has passed or failed. So let me put this into context with our bubble sort test here. As a test case or test input, we have this unsorted input array. And then as a test oracle, we have an incomplete test oracle that basically checks that for this specific input, the array is sorted. In this talk, I'm going to present intramorphic testing, which is a new general whitebox methodology to tackle the test oracle problem. And I first want to outline at a very high level how it works. We have an input I, or a test case, for a program P, and get its output O. And based on this, we derive a new program P prime, for which we get a new output. And then basically we provide a test oracle that checks the two outputs and checks a so-called intramorphic relation between them. Now, before going a bit more into detail about how intramorphic testing works, I first want to explain two other very general methodologies to the test oracle problem, namely differential testing and metamorphic testing. And for all of these methodologies, including ours, these are very high-level ideas whose concrete realizations actually still require domain-specific insights. To put the important thing up front, so the key difference between intramorphic testing and the existing approaches, differential testing and metamorphic testing, is that we are presenting a white box approach, while the others are a black box approach that don't need access to the source code. So what's differential testing? The idea is that we have an input I. We have multiple programs, P1 to Pn, that implement the same behavior. And this basically means that if we execute these programs on the input, we get outputs and we can check that they are actually equivalent. So this is the high-level idea of differential testing. Relating this to our example, one insight that would allow us to do differential testing is that many sorting algorithms and implementations exist, so we can basically validate that they produce the same results. Right? We can have our unsorted input array. We can use implementations like a bubble sort, a merge sort, an insertion sort, and then check that all of this result in this sorted output array. Differential testing is a black box technique, so these implementations could even exist in different programming languages, in different libraries and frameworks that work well when the systems implement the same behavior. So the implementation, I guess, is also quite simple. We basically have these different implementations. we get our input from somewhere. Here it's randomly generated. We invoke our sorting algorithms and then check that they are indeed all produce the same result. And again, similar as for the unit test case, differential testing here would allow us to find this bug. Differential testing has been very influential, so it's one of these techniques that has been applied in a lot of different domains, some of which are here listed on the slides, has been applied for compilers, virtual machines, database engines, debuggers, code coverage tools, and so on. Yeah, next, let's look a bit into metamorphic testing, where the idea is that we have an input I or test case, then we have our program P, we get our output O, and then we derive a follow-up input I prime, for which we get a new output. And the idea of metamorphic testing is that we can validate a so-called metamorphic relation that inspects the two outputs and checks some property between them. Now, one thing that we could check here is that the relative order of sorted elements is maintained when an element is removed from an input array, basically meaning that if we have our array, we can sort it and then remove one random element, which here is 2. And then we can create our follow-up input by first removing the same element, 2, and then sorting it. And both of these, of course, should compute the same result. So this is one application of metamorphic testing here. And I guess you could all implement this quite quickly. And also this approach would allow us to find the bug. So metamorphic testing was first presented in a technical report more than 20 years ago, actually. And in this technical report, the authors used, I would say, quite simple examples to illustrate the approach. And we were actually inspired by this paper and adopted like a similar kind of structure and similar examples also for our intramorphic testing paper here. But the key point is actually, from my perspective, that the initial tech report basically presented a high-level idea, and subsequently a lot of approaches have been actually proposed that had good insights on how we can apply metamorphic testing to various domains. And we basically have the secret hope that our work might also inspire some other work for concrete intramorphic testing applications. Yeah, so differential testing and metamorphic testing are two influential, very high-level ideas to tackle the test oracle problem in a black box way. But I would argue there isn't really a white box approach that is similar in principle that could be used by testers or developers. So we are proposing intramorphic testing as a white box methodology to complement differential testing and metamorphic testing. The key insight is that basically we can think of a program as consisting of multiple components, C1 to Cn, and these components play together to achieve some functionality of the program. And then the idea is that we can take one of these components, we can replace it, we can modify it in some way. And although this is this might be a very local change, it has some anticipated effect on the overall output, on the overall program. And this is then something that we can check in intramorphic testing. Now, for this example, we could realize an intramorphic testing technique by adding a reverse sorting function and then reversing either function's output and check that this should yield the same result as the original sorting function. Right, so if we have our original bubble sort, we might add a second bubble sort reverse function whose output we can then reverse to obtain the same array. And if we implement this, then again, we could find the bug, even if both of these sorting functions actually are affected by the same index bug. We could still find a bug. Of course, this was a Hello World example, so I also want to explain the technique on 3 slightly larger examples before discussing the approach further. And if you're interested in actually playing around with these examples, we also released a Jupyter notebook where you can try this out and where there are some additional explanations. So the first example is about abstract syntax trees and how we can print them. So on the left, you can see that we have this AST that basically represents arithmetic expressions. And using Python, for example, it's straightforward to represent it using different classes for constants, for variables, and operations. Now let's assume that we want to print this AST. Then it's actually not entirely trivial to implement this because we need to take care of this parenthesization. So one way to implement this would, for example, be to check whether the current node is a multiplication. And if one of the children is addition, then we need to add this additional parenthesis. Now, one idea that would enable an intramorphic testing approach here is that we could provide simpler print implementations, namely in prefix and postfix notations, because actually there it's not required that we add this additional parenthesis, and then we can compare that all of them include the same operands and operators. Right, so first we add these additional methods here, which are basically only one lines of code in each case. And then we can invoke all of these print functions. We could strip the parentheses for the infix notation, tokenize them, sort them, and then check that they're all the same. Yeah, continuing with the second example for Monte Carlo simulation. Here the idea is that we have given a rectangle, and then we basically want to sample points in this rectangle and check whether they fall within this circle here to basically approximate the value of pi. And one insight for intramorphic testing here is that fewer samples tend to result in a worse approximation, which basically means that we could, for example, add an additional parameter to our pi approximation function, which basically indicates the number of samples to be taken. And then we could call the function with a low number of samples, also with a high number of samples, and then basically check that that if we use more samples, that we get a more accurate estimate of the value of pi. Then continuing with the last example, the knapsack problem. There the problem is that given a knapsack with a given capacity here, 5 kilograms, we want to maximize the value of items in this knapsack. Because for us it's quite easy, so we can basically pack 2 of the laptops and then fill the remaining weight with the microphones. One way to implement this would be using a greedy knapsack algorithm. And then if you want to test this greedy algorithm, one insight could be that this greedy algorithm should never produce a better result than an optimal algorithm. And this is something that we could check. So we could, for example, implement an exhaustive version of this algorithm and then check that it always performs at least as well as the greedy version. Yeah, so these were the 3 examples that I wanted to provide. We believe that intramorphic testing, like there are many ways to realize it, there are many potential characteristics that intramorphic testing approaches could have. So for example, there might be different granularities in which we apply the approach. This could be single operators, like in the sorting function. It could be entire systems that we are replacing. It could also be microservices. Then in terms of format, whether we do our transformation on the source code level or let's say on the binary level, how we actually realize this transformation, whether we add a new component, a parameter, whether we replace one, whether we do some micrometer programming or so. Then also in terms of completeness, whether it's applicable to any input or only specific ones. And they might also differ in terms of whether they result in false alarms. So I guess for the Monte Carlo example, this would be a bit tricky because it might not always be the case that if we take more samples, we actually get a better estimate. So we basically hope that we don't have answers yet to these questions, which ones are like the better kind of approaches. And we hope that future research might explore different kind of approaches along these dimensions to also explore which ones work well and which ones don't work as well. Then with respect to domains, so I already have presented that basically for differential testing and metamorphic testing, there has been a lot of work, and a lot of this work utilized some insights specific to the domain. And we believe for intramorphic testing, it will be similar. So if you want to apply or develop an approach for compilers, for database systems, for SMT solvers, and so on, you need to use a different kind of insights to enable such an efficient testing approach. In terms of practicality, so what's the intended audience of the approach? If we actually look at users, then I believe that for them, it's easier to use metamorphic testing and differential testing because there the users don't actually need some specific knowledge about how the system is implemented. But for developers, it might actually help them to incorporate their application knowledge into their testing process. So we believe at the moment that intramorphic testing might be a better fit, or it might, like developers might be a better fit than users for intramorphic testing. But also there are still many open questions. For example, how should developers maintain multiple versions of the software? Also, how can we design tooling support to actually support them, right? This could be, for example, the IDE that helps them in this process, or some other tooling support might be necessary. And again, here we also hope that future research will propose approaches to lower the cost of using intramorphic testing and basically reduce the entry barrier. And with that, I want to summarize the talk. So I started with the problem that basically we have differential testing and metamorphic testing as two black box approaches to the test oracle problem, both of which have been very influential, but there wasn't really a very general white box methodology to tackle the test oracle problem. So we propose intramorphic testing, where the idea is that given some inputs and the output of a program, we modify the program in such a way that we can relate then the two outputs in some way and check a so-called intramorphic relation between them. I illustrated the approach using 3 examples, and then also still discussed that we believe that still future research will be necessary to make this actually usable in practice and apply it to different domains. Yeah, with that, thanks for listening, and I'm happy to take questions.
Any questions? Thank you for your talk. I don't see the difference between what you showed and metamorphic testing. All the 3 examples were metamorphic testing. You don't need to know how the code works in your example, but you just need to know what it does. So any testing where you have some input transformation and then an output transformation, that's still metamorphic testing. That's nothing new.
So I wouldn't agree with this because for metamorphic testing, it's a black box approach. So as soon as you modify the program that you want to test, it's no longer metamorphic testing, at least if you strictly take the explanation of the original approach and how people typically understand it nowadays.
Yeah, but you added functions before or after the function under test. You didn't modify the function itself. So I agree. If you have an example that shows where you actually modify the function, then maybe we can see what's new. But your examples also work in the black box way. For example, for the sorting, you pass a comparator function and you change that one, but you don't change the sorting function itself. You just use a different comparator that uses the reverse order.
So I see your point. So I guess you're also saying that the Monte Carlo example is a better fit to illustrate the technique, right? Because there we specifically added a parameter to the function that we want to test.
Okay, yeah, if you assume that the parameter didn't exist. Then I see, okay, so you basically first create a more flexible or parameterizable version of the function under test, and then you apply metamorphic testing in the wider sense as it's understood. Like if you look at Wikipedia, for example, it explains it in that wider sense where you have an input transformation which changes the output in a well-defined way, and then you can compare the old and the new output. One example would be computer vision. You have a photo of something during the day and another photo of the same scenery at night, and the image recognition should give you the same result. So that can be still done as a black box way if you know how the input relates to the output.
Right, but there it's, I guess, the vision software that we would test, right? So we're modifying the original image.
Yes.
Right, and for intramorphic testing, I think we would like to modify the mission software, actually, not the input.
Yes.
But so, I can see your point.
Yes, you can probably make this a bit clearer by trying to find examples where it's more distinct from metamorphic testing. Then it's going to be more apparent what is actually the new part. And I understand that it may take time. So I mean, in this track we are exploring also new ideas. So I'm sure you will come up with examples where it's kind of more obvious where is the novelty in or the difference or metamorphic testing. Thanks.
Okay, thank you.
Well, thank you for your talk. For me, it's not particularly clear why you would want a white box technique. I mean, if there are possibilities where you can apply black box techniques, those are well easier because they are not invasive. Are there particular examples you have in mind where black box techniques as they exist do not work, and your white box technique would offer more possibilities for oracles?
Yeah, that's a good question. So we have thought about this, where this technique would be better, but it's really hard without having a specific application in mind. And I think it just gives people like more opportunities for testing, right? It's similar with fuzzing. There has been black box fuzzing, gray box fuzzing, and white box fuzzing might be, for example, slower in some contexts, and there might be some disadvantages, but it's still a promising approach, right? In some cases, it works better. So, right. But we basically hope that in future research we might be able to answer this question better.
Hi. Since you're doing white box and you're basically modifying programs, one thing that is interesting to me here is that potentially you could use something like program synthesis to come up with transformations and the expected effect, perhaps at the domain level instead of the specific program level, and then use those to do some kind of property-guided intramorphic testing. And then maybe also, now you have these likely specifications, and maybe you can use them to do verification. So I was wondering if maybe this is something that can differentiate these from the black box, where it's like, is it possible that because you go to the white box, you can do something symbolic, basically? Can you bring something new to the automation of testing?
That's an interesting angle. So I guess we haven't thought of any concrete approaches, but it sounds interesting. So I think we should also chat offline and see if we can find a good angle there. Thanks.
Do we have any more questions, perhaps from online? Over there.
So kind of related to the slide that you're showing in the upper right here, like you're creating a modified program. And kind of what I'm curious about is that in all of your examples, you did demonstrate how you would create a modified program, but it didn't seem obvious to me if there's a way to mechanize that doesn't require, say, additional developer time and keeping the modified program up to date. So do you have any comments on that?
Yeah, that's one of the main challenges, I believe. Like you said, adding this additional program variants and maintaining them might actually cause new bugs, and it costs time and effort to maintain them. So I think at this stage we don't have a good answer how we would be able to best solve this. So yeah, I guess future research might or might not provide some ideas there.
Okay, thank you.
Any more questions? Otherwise, thank you, Manuel.
Thank you.